All right. So we're going to start today on Module 2, which is Atomic Structures and Electronic Configurations. So this module is going to be the next step in our understanding of electronic materials. So the last module, Module 1, talked about the arrangement of atoms in solid materials. So we talked about the different types of crystal lattices, like the diamond lattice. We talked about the different types of semiconductors, the elemental versus the compound semiconductors. And then we also talked about like three-dimensional crystals versus two-dimensional crystals. At the end of the lecture last time, and this is not as, there's not as much of this material in the book, but we talked about two-dimensional materials and how they have a trigonal planar bonding, and that can allow you to form sheets of electronic materials that are single atom thick, all right, things like graphene. So atomic arrangement, that's what the last module focused on. Here we're talking about the properties of electrons and how the electrons are arranged in the atoms. So we started with atomic structure. Now we're going to talk about the electronic structure, where the electrons are located, how much energy do the electrons have. Okay, and so the reason we're interested in this is because in order to understand electricity, in order to understand the electrical behavior of a material, we need to understand what the electrons are doing. And it turns out that the properties of the electrons are related to the atomic structure, as you can imagine. So this module is specifically about how electrons are arranged in individual atoms. And the next module will get into how electrons are arranged in solid materials. And what we're going to find out is that in individual atoms, the electrons are arranged in what's called discrete energy levels or discrete energy states. And then in the next module, we'll find out that when you have solid materials, when you have crystalline materials with many atoms, in those cases, that forms something called an energy band. And that energy band structure is critical to how semiconductors behave and where semiconductors get their unique properties. Okay, so this module is going to be, if you've taken a course in quantum physics, you'll see some of the things sound familiar. If you've looked at the Schrodinger wave equation, it'll sound a little bit familiar. We obviously are not going to go into all the depth of all the topics, but I'll just briefly mention, we're going to give just an overview, just enough to understand electronic materials. Okay. Before we get into the specific topics of this module, I just want to bring up this slide. I always like to talk about these concepts from a very simplistic level, just from the foundational level or simplistic level, so that we can build upon that. Okay, electricity is the movement of charges. Okay, and many of you are familiar with this idea. Like, imagine a wire, and then you have electrons flowing through the wire. That's the mental model for electricity that we've been taught since grade school. And that model is fairly valid. You know, electrons moving through a material is how we define current. But you'll notice that there's also this word called holes. Now, electrons, as you know, have a negative charge associated with them. In semiconductors, there's also a charge carrier called a hole, and that charge carrier has an effective positive charge associated with it. So when we look at movement of electricity or the flow of current through a semiconductor, we have to look at the movement of electrons as well as the movement of holes. That's the first thing. Now, the second thing is, when we're talking about current, we have to have a picture in our head. So I just want to remind everybody what that is. So let's just imagine, ignore holes for a second. Imagine that we just have electrons. The electrons are moving through a wire. Okay, where's my pen here? So I'm just going to put, let's say we attach a voltage source, which is a voltage source is like a battery, and we attach it to a wire. Okay, and this is the plus side, and then this is the minus side. Okay, a voltage source is a battery, and a voltage source creates an electric field. And that electric field is denoted with a capital E. Okay, we will talk much more about electric fields later on, but I'm just giving you the overview right now. The electric field is pointed from left to right, from the positive terminal to the negative terminal. So the positive terminal is here, negative terminal is here. Okay, the electric field points from positive to negative. The electrons move opposite the electric field. They move in the opposite direction. So that's why the electrons are moving from right to left. Okay. And they move at a specific velocity. They move at a specific speed. Okay. And so electric current, this part down here, electric current is a measure of the amount of charge or the number of charged particles that pass a point per unit time. So the way you can think about it is imagine that you have this cross section here that I'm going to highlight in red here and just draw across there. Imagine that we cut the wire and we have a cross section there. Well, we're not actually cutting it. Just imagine that we have a cross section there. And we're just looking at how many electrons, how many charges move through that circle per unit time. Okay, and when we do that, we get something called coulombs. A coulombs is a unit of charge. And we can count how many coulombs pass by that circle every second. So coulombs per second. And coulombs per second is an amp. And the ampere is the unit of current. So current is the amount of charge that passes through that cross section per unit time. All right. So the reason I'm bringing this up right now is that I want to put this in the context of materials, electronic materials. So to understand the electrical behavior of a material, we want to know where the electrons are located. All right, so we want to understand where the electrons are located, how much energy they have. This is what we're going to talk about in Module 2. In Module 3, we're going to talk about how many electrons we have. And then in modules kind of spread out between modules 2, 3, and 4, we're going to talk about what direction do electrons move and how fast do they move. All right, so we're going to be building up this model, building up like a very nice picture of how electrons and holes move through materials. It turns out they move using two different mechanisms, drift and diffusion. So we'll get into the details of that later. Okay, so for this module, we're not, we're just doing some of the prerequisites. We're just talking about where the electrons are located and how much energy they have. That's what electronic configuration is. All right, so the specific topics we're going to cover in this module. We're going to start with the atomic spectra. And then we'll talk about how the atomic spectra led to the Bohr model of the atom. Niels Bohr came up with a model of the atom in the late 1800s, early 1900s. And then that remained our main model for the atom for many decades. Starting in the early 1900s to mid 1900s, we've expanded on that model. People like Heisenberg, Einstein have created the quantum mechanical model of the atom. So then eventually we are going to move into that model, which describes a lot of the electrical phenomena in semiconductors. So going from the Bohr model, by the way, is just where electrons are orbiting the nucleus at a specific radius. We'll talk specifically about that. Then we'll get into wave-particle duality. Okay, that's a concept where where physicists started to recognize that sometimes light and electrons, sometimes they behave like waves. When they behave like waves, that means they have certain phenomena that are specific to waves. So for example, they may have like a wavelength and a wave velocity. There may be traveling waves and constructive and destructive interference. There may be things like diffraction patterns. Waves may reflect at a boundary and things like that. So there's certain things that electrons do, there's certain things that light does, photons do, that is wave-like. And there's certain things that light and electrons do that is particle-like. For example, we'll talk about the photoelectric effect. So the basic message here is that light and electrons have this wave-particle duality. Sometimes they can behave as a wave, sometimes they can behave as a particle. There's a concept from a physicist named Debroglie, where Debroglie kind of connected these two concepts together and said, like, particle that's moving at a certain velocity will have an equivalent de Broglie wavelength. So it's sort of a connection between the wave and particle-like behavior. Just to make this more concrete, we'll talk specifically about photons and electrons, what the differences between them are. And then we'll get into the quantum mechanical model and some of the key aspects of it. This is not a physics class, so we aren't going to do a treatment of quantum mechanics similar to what you'd see in a modern physics class. We are just going to go enough on just to understand the basic ideas of semiconductors. So we'll talk about the Heisenberg uncertainty principle. We'll talk about probability density functions, and then we'll get into the Schrodinger wave equation. Schrodinger wave equation describes what we're trying to answer in this module. The question is, how much energy do the electrons have? Where are the electrons located? That's all described by the Schrodinger wave equation. We'll solve the Schrodinger wave function. We'll solve the wave equation and get the Schrodinger wave function, which is the solution to the Schrodinger wave equation. And we'll find the wave functions for the free electron, the potential well, and then we'll end with the single hydrogen atom. And then we'll talk about finally the electronic configuration of single atoms, which is something that you actually saw last module, where you saw that little thing that says 1s2, 2s2, 2p6. That's the electronic configuration of an atom. It tells you where the electrons are located, what orbitals they're located in. And so that'll be a nice way to sum up this module. Okay, so lots to cover here, lots of physics. And again, just as usual, we'll have some examples. There are plenty of points where we'll stop for examples, but if you feel lost or have questions during any of it, please let me know. All right, so we talked about what is electricity, so we'll get going on this now. So the first topic is the atomic spectra. And the way we're talking about this is kind of like a historical perspective. So if we put ourselves in the shoes of physicists or spectroscopists back in the late 1800s. That's what we're going to do here. So we see a phenomena and we are going to try to explain it. And ultimately why we're doing this is because it led to these observations led to the Bohr model of the atom. Okay, that's the first model of atomic behavior. Okay. When physicists come up with models, the models are used to explain behavior. So that's what I want to emphasize here, is that the phenomena that was observed led to the model that was hypothesized by the physicist. Okay, so here's the observation. The observation was that plasma tubes, or neon signs, these are certain types of, there are signs that are signs or light bulbs that are basically tubes filled with gas. Okay, you have a glass tube. If it's first, all the air is pumped out of it, so it's in vacuum, and then you pump in a certain type of gas. Okay, and then you apply an electrical voltage to that gas. That electrical voltage will excite the gas, and the gas will begin to glow. So for context, I mean, you've all seen neon signs. That's how they work. And you've also seen like the long fluorescent light bulbs that you have in basements and things like that. You know, the long fluorescent tubes. Those are also the same concept. Okay, electrical discharges. So what the spectroscopists observed was that depending on what type of gas you put in there, they glow a different color. So we can see pictures of that here from this Wikipedia image. Helium has this sort of reddish color. Neon has more of an orange. Argon is bluish. And then krypton is kind of whitish. And then xenon is kind of purple. Now, it turns out these colors are actually not just one color, but they're actually mixtures of different colors. Specifically, in the late 1800s, spectroscopists, they used prisms to measure the spectra of these gases. So just to remind everyone what an experiment like that might look like. me open a new notebook here. All right, there we go. Give me just a moment here. Okay. All right, so we're all familiar with this concept of a prism. So a prism is to say if you have white light coming in, the prism actually splits up the white light into its constitutive colors. Now I'm going to just draw this in black and white, so I hope forgive me here. So white light will become Roy G. Biv. It'll split up into its constitutive colors: red, orange, yellow, green, blue, indigo, and violet. Okay, so what the spectroscopists can do is they can put a screen here and they can put in a certain light in there and they can see the spectrum that's formed. Okay, and when we look at this screen, so if we look at the screen from this angle, we'll see a bunch of light colors on it. Okay, starting with red, orange, and going all the way to violet at the bottom. Okay. Now, so when spectroscopists did experiments with these, when they took the spectra of these signs or these different gases that they found that the gases glowed a different color. And what that means is that they didn't get all the colors of the spectrum; they only got certain ones. So let's say in a particular, in the case of hydrogen, they saw that they were getting some lines in the red portion of the spectrum. Then they were getting some lines in the yellow portion of the spectrum. They got a line in the maybe in this portion of the spectrum. Okay. Instead of seeing the entire spectrum, ROYGBIV, like the entire rainbow, they would only see lines in the spectrum, on the spectrum screen. Okay, so they started scratching their heads, like, why, this looks red to us. First of all, like, we are actually getting a whole bunch of different lines in the spectrum, which means it's a mixture of different colors. And depending on the type of gas that they were putting in the sign, they would get different spectra. They'd get different patterns of lines on the screen. Okay, any questions on this idea of the spectra? I want to make sure we understand this first before we go on. Okay, no questions on that? Okay. All right, so this is what the hydrogen spectrum looks like. It looked like a bunch of lines like this, and the lines had very specific spacings between them. So this was quite the puzzle. It's quite interesting. So the spectroscopists basically concluded that because you have these lines here, they observed these lines, they said, well, we know how prisms work, so this means that the gas is emitting light at discrete wavelengths, at very specific colors. Okay, and different gases, depending on the gas that you put in, each gas has a characteristic spectra. The spacing between the wavelengths follows a very specific pattern. Okay, so this is kind of like a fingerprint. Every gas had a unique fingerprint. One other thing that the spectroscopists knew at the time is Planck's law. Planck's law is something that related wavelength to energy. So they had discrete wavelengths on the spectrogram. Discrete wavelengths by Planck's law means that they were discrete energies being given off by the atom. Just a reminder of what Planck's law is. Energy is equal to Planck's constant times the frequency of the light. And this is also equal to Planck's constant times c, the speed of light, divided by lambda, the wavelength. So energy and wavelength are inversely related by this equation. So if you have discrete wavelengths that are measured by the spectrogram, that means you have discrete energies that are being given off by the atom. So it's kind of like a fingerprint for the atom. So this led spectroscopists to believe that atoms are giving off energy and discrete energy. The atoms giving off very specific energies, discrete energies. It must be somehow related to the internal structure of the atom. And at some point they came to the conclusion that, oh, it must have something to do with the electronic configuration of the atom. It must have something to do with the electrons being in different energy states. So that was a big advance. That concept was a very big advance in science. That advance led to the Bohr model of light emission and ultimately the Bohr model of the atom. So this is Niels Bohr over on the upper right. This model was first explained in 1913, believe it or not, just like 100 or 110 years ago, not that long ago, if you think about all the things that have happened since then. 1913, Bohr explained the atomic spectra using a planetary model of the atom. So Bohr's theory was this: to connect it to, well, let me tell you about the model first, and then I'll talk to you how it relates to the observations. So Bohr hypothesized that you have an atom, and the atom has a nucleus in the middle, which is not shown here, and the electrons orbit the nucleus at distinct radii. So there are some electrons that orbit at this, what's called energy level 1, and that is a specific radius associated with it. And then the higher energy electrons orbit at energy level 2, and so on, all the way up to however much, higher and higher energy levels. The higher energy electrons occupy a larger, the farther orbits. The orbits that are further away are the electrons that have a higher energy state. The key aspect of the Bohr model is that an atom doesn't have randomly defined orbits. It has very specific orbits at specific radii. So energy level 1 will occur at a very specific radius. Energy level 2 will occur at a very specific radius. And different atoms will have different radii for their energy levels. So how does this relate back to the Bohr model? I have another slide on that. We'll get to that in a second. So the other concept that Bohr came up with is the concept of energy transitions. So he postulated that if you excite a gas like this, excite an atom, you're exciting an atom. When you excite the atom, you basically excite an electron from a lower energy state to a higher energy state. So in this diagram, let's say an electron goes from energy state 1 or energy level 1 to energy level 2. Okay, let me just draw this with the pen. So first what happens is that the electron is excited to a higher energy state by the energy provided by the system. And the second step is that it comes back down. Okay, now you may wonder why does the electron just go back up and come back down? Why doesn't it just stay in the higher energy state? Well, electrons prefer to be in a lower energy state. The only way that you can get an electron out of a lower energy state is to give it some kind of energy so that it can go up to a higher energy state. So you need some energy for step 1 to happen. Okay, once it's in that higher energy state, it doesn't stay there for very long. Okay, and we're talking about time scales of like femtoseconds or something like that. Very small amount of time it stays in the higher energy state, and then it comes back down to the lower energy state. Okay, now when the electron falls back down to the lower energy state, it gives off light. So it gives off a light with energy equal to h times frequency. And this is also equal to hc divided by lambda. Okay, this is also written down here as well. So you have two relationships. So E is equal to HF. And then through the dispersion relationship, you can find that F is equal to C over lambda. So the energy of the light is equal to C over lambda, or HC over lambda, okay? So the energy electron goes back down to the lower energy state, and the difference in energy here, okay, and there's energy 2, energy level 2, energy level 1. So between these two, there's a delta E, a difference in energy, okay? That difference in energy defines what the energy being given off is. And based on that discrete energy, that corresponds to a discrete wavelength here. Okay, so this transition from E2 to E1 is going to give off a distinct wavelength of light. Okay, one other question that students sometimes have is like, okay, the electron goes from a higher energy state to a lower energy state. Why does it have to give off light? Well, energy can neither be created nor destroyed. It can be converted from one form to another. So when the electron is losing energy going from E2 to E1, that energy is being converted into light in this case. Okay. There's other forms that it could be converted into. It could also be converted into heat and other things, but this specific phenomenon is being converted into light. All right, any questions? So let me ask a quick question to gauge your understanding here. Oh, Melvin, you had a question. Sorry, I missed that.
Oh, it's okay. So I had a kind of a question. So just to, I guess, kind of to make sure I understand, I guess you're probably going to ask something, but it goes from E1 to E2, and that's in response to an electric current. So the energy is being transferred from electric current to, I guess, movement to a higher energy state.
Right.
Now, the electric current is still there, right? We assume that this is just some sort of DC source, but it goes back down to the energy state 1, and it gives off the light because it's turning this movement into light. Does it continuously do this over and over again? If the
yeah, absolutely.
Okay.
This process, like step 1, step 2, it is happening very, very quickly.
Okay.
Femtoseconds, the picoseconds, that sort of time scale. Yeah. So, but if you continue to apply the current, this process is happening over and over again with this. It could happen with the same electron. It could happen with a different electron. There's tons of electrons in the system everywhere.
Okay. And I guess one more question. I'm not really a chemistry guy, so it might be more of a basic question. Let's
No
say
problem.
if it started off on E2 and we had E3,
Hmm.
goes up to E2. I mean, sorry, it goes up from E2 to E3, comes back down to E2.
Hmm.
I'm assuming that there's probably E1 may already be full of electrons, and that's why it doesn't continue to go down to E1 since it naturally likes to be in a lower energy state.
Well, no, actually, that could you bring up a good point. If let's say an electron, let's say an electron goes from energy level 2 to energy level 3. Okay, let's say that's the first step. Once it's at energy level 3, it doesn't necessarily need to just come back down to energy level 2. It could even come back down to energy level 1.
See. Okay, all right, that makes
So
sense.
both can happen. So it's a good question, and that's actually what these little this portion of the diagrams are about. So let me just highlight these here. You see these different series, the Paschen series, the Lyman series, and the Balmer series. So the Lyman series, let's start with that. These are all the energy transitions that end at energy level 1. So an excited electron could transition back down from energy level 2 to 1. It could transition from 3 to 1, 4 to 1, and then 5 to 1. All those possibilities exist. Similarly, electron might get excited to energy states 3 or 4, and then they could come back down to 3. So the Paschen series describes all the possible transitions that end at energy level 3, and the Balmer one describes all the ones that end at energy level 2. Okay, so all these different energy transitions obviously correspond to different wavelengths that the electron would emit. And so the cool thing is that these energy transitions, all the different possible energy transitions, correspond to different lines that you can actually see on the atomic spectrum. Okay, so when the scientists made the spectra of the hydrogen atom, okay, this is the hydrogen spectrum that we're looking at here, they looked at these lines, and based on these lines is something that they could physically observe. They looked at the spacing between these lines and determined the corresponding wavelength. From there, they determined the amount of energy transitions you could have from that. And that's ultimately how they determine the different energies of the different energy levels. What's the difference in energy between energy level 3 and 4, and then 4 and 5? Based on these observations, the discrete wavelengths that they observed and the spacings between the wavelengths, they could actually determine the specific energy transitions and actually figure out mathematically what the different energy levels are for each one of these orbits around the nucleus. All right, pretty cool, if you ask me. You go from something you can observe, and then you go back, you use that to figure out something that's on the atomic scale or subatomic scale that obviously would be impossible for us to measure directly. All right, let's continue with this model. So there's some details here that I'm going to have you do in a home. These are equations that describe the Bohr model of the atom. Okay, so the first one here, I'll just note down here, is the radius. So the radius of a particular energy level, that n is the energy level. So for example, you could have R2, R sub 2 is equal to K times 2 squared times this constant. This is a different form of Planck's constant divided by the mass of an electron times the charge of an electron squared. Okay, now I have all of these constants defined down here on the lower right corner. All right, so you could figure out the physical radius of each one of these energy levels by using this equation here. Now the next one here, is there anything else I want to note about that? Okay, I guess the one thing I should note is notice that it's proportional to n squared. Okay, so the radius, it goes up as the square of the energy level. So it's, the radiuses start to increase quickly. Okay. All right, the next point here is the velocity. What is the velocity that the electron is moving at? So if you imagine the electrons orbiting the nucleus along one of those specific radii. So again, you have V sub n, you can say sub n here. The velocity at a specific energy level n is equal to n times h divided by m times r sub n. Okay, it turns out with some math, this is equivalent to q squared over k n h. So q is the charge of an electron, and that's given down here, 1.6 times 10 to the negative 19. K is a constant equal to 4 pi times epsilon naught, where epsilon naught is the vacuum permittivity. N is the energy level. And then H with the bar across is just a different form of Planck's constant. Okay, so we figured out the radius and the velocity, and now the energy. Okay, the energy is an important concept, maybe slightly less intuitive than the other ones. But the way that I like to think about it is this, okay? Imagine that the different electron, depending on which energy state, the energy level that the electron's orbiting in, it has a certain radius, right? Radius can be given, each energy state has a certain radius, which can be given in like meters or angstroms. The electron has a certain velocity in meters per second, and then it has a certain, each energy level has an associated energy. And that energy could be given in joules, for example. So the energy of a particular state, E sub n, is equal to mv squared over 2 minus q squared over krn. We're not going into the details of where this comes from. And then you have a simple formula for it here. M times q to the fourth divided by 2 times knh squared. So then the energy transition is the last one. So if an electron transitions from a high energy state, N2, to a lower energy state, N1, then the change in energy, this delta E that we're talking about here, this delta E is given by this equation. Okay, you notice you have 1 over n squared, 1 over n2, 1 over n1 squared, n2 squared. N2 is the energy, the higher energy level. So it could be, let's say we're talking about a transition from energy level 4 to 3. So N2 would be equal to 4 and N1 would be equal to 3. And then you have to plug in these other constants. So you can clearly see that the energy transitions are dependent on the energy level that you're at. Okay. I would like for all of us to, you'll have a homework question on that. So we won't spend any more time in class doing it right now. But are there any conceptual questions that I can help answer? Okay. All right, good.
I guess I just got just one quick question.
Sure.
You probably already mentioned it.
Mm-hmm.
Velocity, is that the velocity at which the electron orbits, or is that the velocity at which it changes states?
That's the velocity at which it orbits.
Okay. All right.
Yep. Yeah. Good question. All right. So to sum up then, the Bohr model is used to explain the discrete atomic spectra. So scientists saw this. Okay, and through a lot of smart thinking, they related this observation back to the Bohr model of hydrogen. And so the way that we think about it now is actually in the opposite direction. We think about, okay, this is the model, the Bohr model of hydrogen. There's these distinct energy levels. So there's distinct energy transitions. And so we can figure out all the possible combinations of transitions there are. So energy level 2 to 1, 3 to 1, 4 to 1, 5 to 1. And then we can consider all the energy transitions that end at energy level 2, 3 to 2, 4 to 2, 5 to 2, and then and so on. So we have these different series that emerge, different energy transitions, the Lyman series, the Balmer series, and the Paschen series. And each one of them have corresponding lines on the hydrogen spectrum that are observed. And this is not just for hydrogen. Okay, it's related to any atom. Okay, so they do the same experiment for xenon and see a different spectra. Okay. All right, so the Bohr model was great for explaining discrete spectra, but as I will note here, the Bohr model works well for hydrogen, but for more complex atoms, the quantum mechanical model that we'll talk about later is going to be more appropriate for that. Okay, so now we are done talking about the Bohr model and atomic spectra. Now we're going to talk about wave-particle duality. Okay, and that's sort of a precursor to get into the quantum mechanical models. All right, so we're just going to talk about light energy here. So light energy is contained in discrete units called photons, and photons can behave both as a particle and as a wave. So light, we think about light. Light can behave both as a particle and a wave. We'll give some examples of that. Also, electrons and neutrons and other types of particles also exhibit this type of dual behavior where it has some wave-like behaviors and some particle-like behaviors. So what do I mean by that? If we think about the wave nature of light, think back to your physics class. Like, what do waves do? You may remember, when you talk about waves in a physics class, you say like, well, the wave has amplitude, it has wavelength, waves can interfere with each other, like constructive and destructive interference. Diffraction can happen, meaning like the waves can bend at a boundary and you can form these diffraction patterns. If we'll talk an example of that. Polarization can happen where the waves, the fields of the wave become aligned at a certain angle. And refraction can happen. Refraction is where light, for example, bends at a boundary. Okay, so those are all explained by basically saying that, oh, light is a wave. But there's other phenomena of light that can only be explained by explaining as a particle. So for example, the photoelectric effect can be explained by the particle nature of light. Some aspects of reflection and refraction can be explained by the particle nature of light. This is where we think about light as being a particle that's moving through space. Okay, and so these two things don't just apply to light, they apply to other particles as well. So just to be clear, when we think about light, the discrete packet of light is called a photon. The smallest packet of light you can have is called a photon. So similarly, there are these units called electrons, neutrons, and other particles, which are the analogs of photons that also exhibit this sort of same dual behavior, some wave-like properties and some particle-like properties. So let's get into some aspects of wave and particle behavior. Let's remind ourselves what wave-like behavior is. So when we think about waves, you've learned about waves in your physics class, and the way they're often described is that you draw like a sinusoid here. A sinusoid has a certain amplitude a peak amplitude. It has a certain wavelength, a lambda. Lambda, this is the distance between two peaks of the wave, or maybe between two troughs of the wave. Okay, and it can be described by this equation: f of x is equal to a, the amplitude, times sine of kx. All right. And so k is related to lambda. So the way that it's related to lambda is this wave number here. K is equal to 2 pi over lambda. Okay, so lambda would be 2 pi over k. Now k is the wave number. And the way that we define the wave number is that if we say if the wave was standing still, okay, we're not talking about a traveling wave yet, we're just talking about a stationary wave. So if the wave was standing still, how many waves could you fit in a meter? That is the definition of the wave number. So the wave number is intimately related to the wavelength. It's inversely proportional. Higher wave numbers mean smaller wavelengths. Okay, so far so good. So that's a stationary wave. Now a traveling wave, bring this up, come on, there we go. Traveling wave looks like this. So just imagine that same wave that we had there, but now that wave is moving through space. It's moving at a specific velocity. So this equation now, this f of x equation, which was just a function of x, is now a function of x and t both. All right, does that make sense, hopefully? All right, so a traveling wave is given by function f of x comma t. And the equation for a traveling wave, it is just expanding on the stationary wave equation. You'll see some aspects are similar. Oops. You still have an a there. The a describes the amplitude of the wave. And you can still call it by a sine function. You can also use cosine, but here we're just describing a sine. Now this kx that we had for the stationary wave, that kx has now become kx minus omega t. Okay, so that's the change in the equation. So the kx is the same as before. That's defined as the wave number. So if the wave was standing still, how many waves could you fit in a meter? And that k factor describes that aspect of the wave. So it's related to the wavelength, as I said. So if you look at the distance between the troughs, the physical distance between the troughs on the x-axis is the same thing as above here. It has a second term, the angular frequency. So the angular frequency, the way to think about it is if I stood at a point, so you see where my mouse is, okay? If I stood at that point and I just counted how many waves were passing by me every second, that is the angular frequency, and that is given in radians per second. So an entire wave is 2 pi radians. So if a full wavelength passes by me in a second, that's 2 pi. A full pass of the wave will give me 2 pi radians. Okay, so the angular frequency will be 2 pi times f, and f is the frequency in hertz. So just to clarify, f would be like, you can say, well, there's 5 waves that are passing by me every second. So f would be equal to 5 hertz. But the angular frequency will be 2 pi times f. So 2 pi times 5. So that'll be 10 pi radians per second. All right. And then finally, the velocity has to do with both of these. The velocity is how fast is the wave moving through the medium. So here, if we just take this trough and I'm following with my mouse and see how fast it moves in this horizontal direction. That is the velocity, the physical velocity. Okay, and the velocity of a traveling wave is given by lambda times f. Wavelength times the frequency is equal to the velocity. And if you don't, one way to confirm that is just to remind ourselves that the wavelength is given in meters, and the frequency is the units for frequency is 1 over second. So velocity is just meters per second. Okay. Now, if we use the our knowledge of wave number and angular frequency that we have from these two equations up here, we can basically find that the velocity is equal to omega, the angular frequency, divided by the wave number. Omega over k is equal to the velocity. Okay, so we have a nice way of relating the velocity of a traveling wave just by looking at these two numbers in the equation. Velocity is equal to omega over k. Okay, so I encourage you to just play with these numbers. You know, you can find a traveling wave simulator if you'd like, and just put in different values of k, and you can see how the wavelength will change. Put in different values of omega, and you'll see like how fast, like, you know, how many waves pass by a given point per second. So you can basically change the velocity and just get a feel for it. So this is some fundamentals of what a wave is, mathematically what a wave is. In terms of wave-like behavior, we know that light behaves like a, you know, we have, let's say not just light, but electromagnetic energy has wave-like behavior. Okay, the electromagnetic spectrum is an example of the wave-like behavior of light. Now it says wave-like behavior of light, but you know, it's really applies to any form of electromagnetic radiation. We talk about, when we say light, we're often talking about the visible portion of the spectrum. So light is stuff that we can see, you know, red, orange, green, blue, indigo, violet. That's only a portion of the electromagnetic spectrum, but there's other portions of it as well that we can't see. And those portions are sometimes called radio waves, gamma waves, ultraviolet rays, so all things like that. So they're all the same, and they're all different forms of electromagnetic radiation, which are waves composed of electrical and magnetic fields. Okay, so imagine that we just have electromagnetic radiation, and that radiation occurs at different frequencies and wavelengths. These are the two equations that I mentioned earlier. I'm sure you're familiar with these equations from physics. Just to review them, the dispersion relationship on the bottom here, C is equal to the frequency of the light times the wavelength of light. Okay, C is the velocity of light. That's fixed at 3 × 10⁸ meters per second. F is the frequency, and lambda is the wavelength. So the frequency and wavelength are inversely related. The second equation is Planck's relationship. The energy of the light is equal to Planck's constant times the frequency. So what that means is that high frequency light will have high energy. So if we consider the different portions of the electromagnetic spectrum, on this end, we have low energy, high wavelength light. So F is small and wavelength is large. So that's this portion of the spectrum. So radio waves have wavelengths that are on the order of 10 to the third. Now, I don't know if you're aware of that or not. Radio waves are on the order of kilometers. The wavelengths for those, huge wavelengths. Okay. So that's corresponds to a frequency of about 10 to the 4th. Now, when we start going to slightly smaller wavelengths, higher frequency, higher energy, we can get to the microwave portion of the spectrum. Now, this would be things like microwave 10 to the -2 would be centimeter scale. So things like butterflies would be on the centimeter scale. Microwaves, which is basically, there's a few different types of electromagnetic radiation that are in the form of microwaves. Besides the microwave oven, yeah, microwave oven are microwaves. They have wavelengths on the order of centimeters. Can anyone guess some other ones?
Is Wi-Fi one? Or like Bluetooth?
Yeah, exactly. I'm just going to put this down here. I'm going to put 10 to the 9th. So this is gigahertz. Oops. Thank you, Janan. So these are gigahertz frequencies. Microwave wavelengths corresponds to gigahertz frequencies. And so the Wi-Fi portion of the spectrum, so Wi-Fi and Bluetooth are all operate close to 2.4 gigahertz. Certain types of Wi-Fi now do 5 gigahertz. So that's all in the microwave portion of the spectrum. Okay. Now, why are radio waves and microwaves used for communication? Well, it turns out that lower energy radiation, longer wavelengths penetrate better through material. So radio waves and microwaves, they can go through walls. In fact, it can go through some concrete walls. And whereas higher frequency, higher energy radiation does not go through walls. So that's one of the reasons why we like using low energy, high wavelength electromagnetic radiation for communication. If you get out into the radio portion of the spectrum, it even penetrates Earth's atmosphere. And of course, this is great for satellites. The Voyager spacecrafts and other spacecrafts, they communicate through this portion of the spectrum. Thought you might find that interesting. Okay, so moving on, then there's the infrared portion of the spectrum. This is where the wavelengths are on the order of 10 to the negative 5, or the size of the point of a needle. This corresponds to greater than terahertz frequencies. And infrared light is used, infrared imaging is used for night vision, things like that. Then we get to the visible portion of the spectrum. This is where the wavelengths are on the order of micrometers. This is our Roy G. Biv. This is the wavelengths of the light are typically on the sizes of cells. But you know, we observe, our eyes can observe this type of electromagnetic radiation as different colors of the spectrum, different colors that we observe. Going on to higher energy radiation, you have the ultraviolet radiation, 10 to the negative 8, X-ray 10 to the negative 10, and gamma rays 10 to the negative 12. Okay. I just want to note that the higher the energy of the radiation is, the more hazardous it is to human health, because high energy radiation can actually cause molecules in our body to change shape and to actually get damaged. Ultraviolets and X-rays and gamma rays, it can damage our DNA, the material, the nucleic acid material that we have in our bodies that basically is a blueprint for how cells replicate and things like that. So if we mess that up, you know, you can get things like cancers and things like that. This is why we try to protect ourselves from UV rays, and we limit the amount of X-ray radiation that we get if we take X-rays in hospitals. And gamma rays, we fortunately don't see that at all on Earth, or very little. Okay, but this is the kind of radiation that unfortunately happens from like nuclear fallouts and things like that. So that can be very dangerous to humans. So in terms of wavelengths, ultraviolet is on the scale of molecules, X-rays are on the scale of atoms, and gamma rays are on the scale of atomic nuclei. Okay. So the one more example of wave-like behavior are diffraction patterns. So again, scientists explain some phenomena that they can observe through the wave model of light. So this is a classic physics experiment where you know, you have photon diffraction, the single slit diffraction, double slit diffraction. If you have light that's kind of coming through from a laser beam, and then you have one opening. Okay, you have something blocking the laser light, these portions here, and then you have an opening in there. And then you let laser light go through the opening, you'll see a diffraction pattern show up like this. The diffraction pattern will have something that's very strong in the middle, and then it'll have regions on the outside, a second node here on the outside, which is also bright, but not, it's not as bright as the center one, but it's also not completely dark. Okay. So if light didn't have a wave-like behavior, you'd just see one blotch of light showing up on this diagram. But what's observed instead is that you have some light on this end, some light in the middle, some light on this end. So basically, this is what's called an interference pattern. There's some regions where the light waves will constructively interfere. That's where you get this bright spot. And some regions where it will destructively interfere and you get nothing. And some regions where it'll constructively and interfere again, and you have another bright spot. So this type of phenomena can only be explained by the wave-like behavior of light. Another similar experiment is the double slit diffraction experiment. This is where you have your mask has two openings in it. So you can have two waves of light penetrating through the openings, and those two waves of light can interfere with each other. And in this one, you get a really cool interference pattern, like you get a series of bright spots and dark spots, bright spots and dark spots. In the bright spots, they constructively interfere. In the dark spots, they destructively interfere. Okay. Now, there's obviously a lot of math that can go into this to describe like how these spherical wave fronts interact, and we can mathematically calculate how wide these diffraction regions should be, what should be the pitch between two constructive zones. But it's all mathematically calculatable, and those calculations correspond to what is observed. Okay. One other phenomena that you may be familiar with or may not be is called electron diffraction. This is a cool image from Crane's Modern Physics book. Electron diffraction is used in something called X-ray crystallography. This is where we shoot X-rays into high energy X-rays into an atom, and the X-rays bounce off the atom and they're detected. And they form certain patterns, just like these single and double slit experiments. The light, the X-ray, the radiation, it actually hits a portion of the atom and then it bends off in a certain direction. So you have different, radiation coming in from a certain direction, but that radiation is getting bounced off in different directions due to the atomic structure. And what you end up getting is these diffraction patterns, electron diffraction patterns. And based on those, the patterns that you see, the constructive and destructive interferences, the spacing between these dots, you can actually mathematically reconstruct what the atomic structure of the atom, of that molecular structure of this crystal is. It's a really cool technique. If any of you have seen biology textbooks where they have these beautiful pictures of proteins and like, down like this is exactly what the protein looks like, that's because we have things like X-ray crystallography. Very, very cool. All right. Any questions on wave-like behavior?
No.
Clayton? Okay. Anyone else? All right. Nope. Okay. So let's get to particle-like behavior now. We have 25 minutes, so I think we can cover that. So particle-like behavior, we can think about a ball moving through space. And in the context of light, we can think about a photon of light moving through space, kind of like a tennis ball. So I just want to review what particle-like behavior is, because we are going to revisit it in this class when we do some calculations with it. So I think it's worth it to revisit some fundamental concepts from physics. Gravitational potential energy and electrical potential energy. So anytime you have particle-like behavior, the particle can have a combination of kinetic and potential energy. So we'll talk about both here. We'll start by talking about potential energy. We'll talk about how that potential energy is converted to kinetic. Very simple example. You have a tennis ball, and that tennis ball is held at a height h above the earth. And then you just drop the tennis ball. Okay, so what I want you to understand here is that the tennis ball has some gravitational potential energy because it's held at a height h above the earth. So the gravitational field is going to exert a force on the object and causing this object to accelerate. And as that happens, this gravitational potential energy U is converted to kinetic energy K as the object accelerates. So at the top, before we release it, there's no kinetic energy, right? Kinetic energy is movement. So there's no movement yet. So all the energy is gravitational potential energy U. And when we let the ball go, the ball is going faster and faster and faster. So the kinetic energy increases and the gravitational potential energy decreases. All right, so I want you to look at the, we'll look at the equations for that. At any point in time, the total energy is equal to the kinetic energy plus the gravitational potential energy. All right, so let's look at the specifics of this. So there's a force of gravity. You let the ball go. That force of gravity will cause the ball to accelerate. The force of gravity is equal to the mass times the acceleration, ma, and that is equal to mg. The acceleration is the gravitational constant, which on Earth is 9.8 meters per second squared. So if we were to calculate the velocity as a function of time, so initially the initial velocity of the ball is 0. So this v0, the initial velocity would be equal to 0. And then to that you add an integral of the acceleration with respect to time. The integral of a dt, and you take the integral from 0 to t here. So the ball basically goes faster and faster over time. The way we define potential energy, gravitational potential energy, is defined as mgh, the mass of the object times the gravitational acceleration times the height. So from this, you can kind of see that this is dependent on height. The higher we hold the ball up, the more gravitational potential energy it has. And as the ball moves towards the Earth, it's starting to lose that gravitational potential energy. So as the ball falls, gravitational potential energy goes down, kinetic energy goes up. Kinetic energy is equal to 1/2 mv squared. This is a fundamental rule from physics. So as the velocity is increasing, the kinetic energy is going up as the square of the velocity. The gravitational constant we have here, right? So this is gravitational potential energy. So you can see the relationship between kinetic and potential energy. Reason we talked about that, reviewed that, is I want you to see the same situation, the analogy of that situation in an electrical system rather than a gravitational system or mechanical system. So in an electrical system, the electric field, rather than the gravitational field, the electric field is what exerts force on a charged particle and it causes it to accelerate. So there's no gravity here. Similar to before, electrical potential energy U is converted to kinetic energy K as the particle accelerates. Same concept. At any point in time, same as before, the total energy E is equal to K plus U. Okay, K is the kinetic energy, U is the electric potential energy. So the way that this system would look like, it's like this. You have a voltage source, which is basically a battery, and the battery is connected to a positive plate, one metal plate up here, another metal plate down here. So a metal plate, just a piece of metal, flat piece of metal, okay? So this is separated by a distance d. When you connect the battery, what's going to happen is that the top of the battery, or the top plate, is going to acquire a positive charge, and the lower plate is going to acquire a negative charge, and separated by a distance d. Okay, this is not a class in electromagnetics, but we should touch on some of this stuff because it will become important in this class. When this type of situation happens, you have a buildup of positive charge on one plate, buildup of negative charge on the other plate. There's an electric field is created, okay? And that electric field is what exerts force on the charged particle. Okay, so the electric field is serving as what the gravitational field is doing here. Okay, we are supplying that electric field by supplying a voltage here. All right, let's look at these some of the specific equations. So the voltage and the electric field are related by this equation, V equals ED. The voltage is equal to the electric field times the distance between the plates. The electric force is equal to EQ, and that is equal to the mass times acceleration. So let me just get the charged particle on here. So imagine that we have a charged particle within this electric field. So what happens is the fundamental concept. If you have a positive charge in an electric field, the positive charge moves in the same direction as the electric field. So this positive charge is going to move downwards. If you had a negative charge, the negative charge would move opposite the electric field in the opposite direction. Okay, so we're comparing a single charge Q to the tennis ball that we had here. In the case of the tennis ball, there's a force of gravity. In the case of in the electrical system, there's the electric force. And that electric force, F sub E, is equal to the electric field times Q, which is the amount of charge. A single proton has a charge equal to 1.6 times 10 to the negative 19 coulombs. Okay, so you can figure out the electric force here. And this electric force is also equal to MA. So think about it this way, is that the electric field is creating a force, which is E times Q, and that force is causing the charge to accelerate. And it's accelerating, you can calculate the A based on what the E is. What higher the electric field, the more acceleration you're going to get. Okay, and keep in mind that the mass is something that would be fixed, you know, the mass of a proton. Okay. Velocity equation is the same as before. V of t is equal to V0 plus the integral of the acceleration. Okay, both particles are accelerating due to a force. The type of force is just different. So in this system, the potential energy, instead of being equal to mgh, the electric potential energy is voltage times Q. Kinetic energy is the same as before. It's 1/2 mv squared. And just one constant to be aware of, Q. This is the charge of an electron. It's the charge of a proton. The proton has charge 1.6 times 10 to the negative 19 coulombs. An electron has charge negative 1.6 times 10 to the negative 19 coulombs. All right. So the way that you can imagine is if we were to put a single charge within this electric field, then that single charge would just get accelerated and go faster and faster and faster as we move down, as it moves through this field. Okay. All right, so examples. I'll go through these examples really quickly, just in the interest of time here. Let me just delete these for the time being. These are simple calculations, so we don't need to spend too much time on it. So gravitational potential energy, if we want to find the gravitational potential energy of a tennis ball, which is 2 ounces, a tennis ball that's held at a 2-meter height, the potential energy is just mgh. The mass times the gravitational constant times the height. So this is the mass of the tennis ball, 0.057 kg times 9.8 meters per second squared. That's the gravitational constant on Earth. And then the height is 2 meters. So we can calculate here that it's 1.11 joules. A couple things to note. Remember, we're using the MKS system here, meters, kilograms, second. So the mass is in kilograms, acceleration is in meters per second squared, and distance is in meters. The units for energy in the MKS system is joules. So this contains 1.1 joules of energy. Sorry. Now, if we go to the electrical system, If we find the electrical potential energy of 1 coulomb of charge at 1 volt, we use the again, fairly simple equations. The electric potential energy, the energy is equal to Q times V. So 1 coulomb of charge. So imagine our charged particle has 1 coulomb of charge multiplied by 1 volt. That's the voltage. Q is the charge of this particle, and the voltage is the voltage that we put across the two plates. So that would be one joule. And then another example is find the electric potential energy of 1 proton of charge at 1 volt. So the only thing we do differently here is that the Q, instead of being 1 coulombs, it's 1.6 times 10 to the negative 19 coulombs. You still multiply that by 1 volt. So in this case, the electrical potential energy is 1.6 times 10 to the negative 19 joules. Okay, just so you kind of have like a physical idea of like what's going on here, like how much energy is 1 joule and how much charge is 1 coulomb. It's helpful to just think about that a little bit. If you held a tennis ball 2 meters above the earth, that you basically have 1.11 joules of energy that tennis ball has. So you might look at this and say like, well, this electrical system has similar amount of energy, about 1 joule. But like we have to think about what physically this means. Voltage, like a one volt is not really that much voltage, right? We know that like a typical cell phone battery has like 3.6 volts. You know, a AA battery has 1.5 volts, you know, so it's 1 volt is no big deal, but 1 coulomb of charge, that's a lot of charge. Okay, so a lightning bolt is 15 coulombs. Okay, just to give you a sense of that. In terms of battery capacity, 1 AA battery can hold 5,000 coulombs of charge. So it actually can, you know, that's a AA battery actually holds quite quite a bit of charge. So 1 coulomb of charge is actually quite, you know, quite a bit. Another way to think about it is that a single proton is 1.6 times 10 to the negative 19 coulombs. So you'd need like 10 to the 19th protons to make 1 coulomb of charge. So just something to keep in mind. Okay, so I hope you have an idea of like these different amounts of energies now. So I want to talk about the other aspects of particle-like behavior, the photoelectric effect. I think we have like 10 minutes here, and then perhaps we'll get to the de Broglie thing. We'll touch on it today and we'll revisit it next time. Okay, so particle-like behavior. This is, you know, particle-like behavior is when you can imagine something like moving in space and bumping into things. You know, that's particle-like behavior. And so Einstein's won the Nobel Prize in 1921 because he showed that light can actually have particle-like behaviors. Prior to 1921, all the experiments and models kind of assumed that light was just a wave. So the photoelectric effect, the experiment that Einstein did, was that he used light to knock electrons off a piece of metal. So he basically took high energy light, shined it at a metal, and he had a clever way of measuring whether electrons were coming off or not. Okay, and the way that he actually measured it was kind of like an electrical setup here where he had like an electron detector here. And when the electron hit that detector, it created a little pulse of current going through this circuit. Okay. First of all, he had to put this whole thing under vacuum, because if this experiment is done in air, the electrons will bump into air molecules and then you won't be able to measure them. Okay. So, you know, conceptually simple experiment, deceptively simple, but the cool thing is like how he took the results of the experiment and he backed out something called the photoelectric effect. Very, very cool. Okay, so here's how the photoelectric effect works. So think about light as a bunch of photons, and the photons you can think about the particle. Okay, so light hits, each photon hits the metal, and if you hit that hard enough, if you hit it hard enough, if the collision has enough momentum, enough energy, then it will knock off an electron. Okay, so if you think about this, like think about just throwing a tennis ball at a wall and you want to knock a part of the wall off. That's the way that I like to think about the photoelectric effect. Kind of a simplistic model. But the way that we can think about this is that you need to, if you want to knock off a part of the wall, is that you have to have a minimum energy. You have to have sufficient energy in order to eject an electron. Okay, and the energy is equal to the work function of the metal. Okay, the way that the wall analogy, if it's helpful to you or not, you can think about it as being kind of like the stiffness of the wall. You need how fast do you need to throw that tennis ball at the wall in order to break off a chunk of the wall? Okay, the analogy here is that photons will, if the photon has enough energy, it can break off an electron, and that minimum energy is equal to the work function of the metal. As I mentioned before, Einstein detected the energy of the electron using an electrostatic plate. That's what this line here is. And when the electron reached that electrostatic plate, it would, it could create a pulse of current that he could measure. Not just one electron, maybe there are many electrons going in there. Okay, so this is kind of the model here. So what's happening here is that he is increasing the frequency of the frequency of the light. Okay, so as the frequency is going up, the energy is also going up. So this is the energy of the light that he's shining on the metal. And the y-axis, this is the kinetic energy of the ejected electron. And that's what he's measuring using his electrostatic plate. So in the experiment, you start off with low energy photons. No electrons are ejected. So you end up getting just this. Zero kinetic energy of emitted electrons. There's no emitted electrons. Once you get to here, once you get to, once the energy is equal to Q times the work function of the metal, then the electrons start getting ejected. And as you increase the energy further, the electrons that are ejected, these guys have more and more kinetic energy, and that can be detected by this circuit here. So Einstein found that the more energy that you put in, the more energy that you, more energy of the incoming light, first it has to overcome the metal work function, but then beyond that, the more energy of the light, the more energy of the electrons that also bounce off. Okay, it's like the harder you throw the tennis ball at the wall, the faster the chunks of the wall will fall off. That's one way to think about it. Okay, and specifically this equation, the kinetic energy of the electrons 1/2 mv squared is equal to hf minus q phi. Hf is Planck's constant times the frequency of the photon coming in minus q times phi, the work function. Phi is the work function of the metal. So this was an extremely important experiment that revealed something about atomic structure. It revealed that electrons can, and the electrons can be ejected out of metals. That means that the electrons are not bound completely. They can actually be removed or ionized. But it also showed the particle-like behavior of light. Light can do this. How could a wave like physically like remove an electron? So he's mentioned that this is more like a particle-like behavior. So the last thing I'll mention today is this Debroglie concept, and we'll have to come back to this next time in class since we're just about out of time here. So there were, at this point in the 1921, Einstein won the Nobel Prize for the photoelectric effect, And prior to that, there were all these experiments that showed the wave-like nature. So at this point in time, there was experiments that showed particle-like behavior and experiments that showed a wave-like behavior. So de Broglie's equation relates both of these behaviors together. And the story is that this de Broglie was a French physicist, and he came up with this extremely simple equation with very little experimental proof. But it turned out that he was right, and it turned out to be one of the most influential equations in modern physics. So the de Broglie equation basically said that any moving particle has an associated wavelength. So think about that for a second. This is an equation that is bringing together the particle-like nature and the wave-like nature. It's saying any moving particle that has a velocity v, so I'm just highlighting the equation here. If a particle has a velocity v and a mass m, then using this equation, you can figure out the associated wavelength. The de Broglie wavelength lambda is equal to h over mass times velocity. And mass times velocity, by the way, is the momentum of a particle. Okay. What a cool, what a simple and cool equation that nicely and very simply relates the particle and wave-like behaviors together. So I just want to just note here that this wave number, I think we showed this on a previous slide, but the reason I'm showing it again here is so that a lot of times this momentum element P is expressed in terms of a wave number. So this wave number K is equal to 2 pi over lambda. This is what we defined before when we were talking about traveling waves. And then, so then based on that, we can reformat P, the momentum. The momentum is equal to h over lambda. And lambda is 2 pi over K. And h over 2 pi is equal to this a different version of Planck's constant times K. So just a little bit of math here. And what this is showing is that the momentum of a particle, P equals mv, the momentum is equal to Planck's constant times the wave number. Okay, and the wave number was, as I mentioned, the distance between, if the wave is standing still, what is the physical distance between the troughs of the wave or the crests of the wave? Okay, there's just a little bit of a note on a wave number, but the main point we want to get across here is the de Broglie wavelength. Okay, so the de Broglie equation is basically saying that the wavelength, every particle that moves at a velocity v has an associated wavelength, and you can clearly see that they're inversely related. So a particle that's moving with very fast velocity will have a small wavelength. And a particle that's moving with slow velocity will have a large wavelength. The other big thing here is the mass. This is probably the most important. I've left the most important point to the end. This mass plays a very important role in the wavelength as well. It's on the denominator. So you might think like, well, any moving particle, okay, I'm driving my car down I-75. Does it have a de Broglie wavelength? In fact, it does. It does, but it's so small that we can't measure it. Your car has a lot of mass, right? The m is very large. When m is large, this wavelength is tiny. Okay. It turns out that in order for the de Broglie wavelength to be something significant, something that we can actually measure, something on the order of microns or nanometers even, you have to the mass of the object has to be very small, and the velocity has, the mass has to be small enough, and the velocity has to be, mv has to be small enough so that the wavelength is large enough. Let's put it that way. Okay. Since we're out of time in today's class, we'll start with this next time, but just go ahead and do these two problems before class next time. I'd request that you do that by Monday. I know you have your homework assignments, but this shouldn't take very long to do. So I just want you to see the de Broglie wavelengths, like calculate the de Broglie wavelength of a 7-gram bullet traveling at 10 meters per second. So we like to think of bullets as being the mass is small and the velocity is large, but just go ahead and calculate the wavelength of that. And then the second example is calculate the de Broglie wavelength of an electron with energy 1000 electron volts. And I just want to mention that electron volts, this is a unit of energy. And then 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Okay, so just remember that when you're doing this problem. So the hint I'm going to give you is first calculate the electron velocity. We have the kinetic energy equation, so you can use that to calculate the electron velocity, and then use a velocity to calculate what the de Broglie wavelength is. And you're going to see there's a huge difference between the de Broglie wavelengths of a bullet versus an electron. Okay. So we will, looks like we're out of time today. Any questions? Any questions? Okay. All right, looks like we have no questions then. Just a reminder then, I'll stop the recording here and we'll see you in class on Monday.